Hello everyone, I am Dr.G.B.Chandra Mouli, Assistant Professor of Mathematics, Freshman Engineering Department, Aditya University. So the topic is partial differential equations. At the end of this lecture, student will be able to know the definition of a partial differential equation and will be able to solve linear partial differential equation of the first order by Lagrange's method. Now, definition of a partial differential equation. A differential equation is said to be partial if the derivatives in the equation are the partial derivatives, which means derivatives of one dependent variable with respect to more than one independent variable. Example, dou u by dou x plus dou u by dou y is equal to 0. So, here u is the dependent variable which is a function of two independent variables x and y, and we have partial derivatives of u with respect to x and y in this equation, and it is a partial differential equation. And similarly, the second example is dou square y by dou x square is equal to 1 by c square dou square y by dou t square. So, which is a one dimensional wave equation, and it is a partial differential equation in which y is the dependent variable and x and t are the independent variables. Similarly, third equation is one dimensional heat equation where u is the dependent variable, is a function of x and t, and the fourth equation is the two dimensional Laplace equation where u is the dependent variable, is a function of two independent variables x and y. We can define the order of the differential equation or order of the partial differential equations as the order of the highest derivative that is present in the equation. So, in the first equation, where the highest derivative is of order 1, so order of the PDE is 1, and in the second, third and fourth equations, the order of all the highest order derivative in all these equations is 2, so order of all these equations is 2, and a differential equation is said to be linear, or the second definition you can take is the degree of the PDE. So, degree of the differential equation is the degree of the highest derivative that is present in the equation with respect to the dependent variable and its derivatives. So, in all these examples, we have first degree dependent variables and their derivatives. So, degree of all these equations is 1. Next, solution of partial differential equation. Any relation between the dependent variable and the independent variables not containing their derivatives and which satisfies the given differential equation is called solution or integral of the partial differential equation. Next, general solution of PDE. A solution which contains maximum possible number of arbitrary functions is called general solution or integral of the PDE. In another manner, in this solution, the number of arbitrary functions in the solution, if it is equal to order of PDE, then such a solution is said to be general solution. So, if the order of the PDE is 1 and if the solution contains one arbitrary constant function, then that solution is called general solution, and if the order of the PDE is 2 and the solution contains two arbitrary functions, that solution is called general solution. Next, complete solution. A solution which contains maximum possible number of arbitrary constants is called complete solution or complete integral, here the order of the PDE is equal to the number of arbitrary constants present in the equation, then such a solution is said to be complete solution. Suppose if the order of the PDE is 2 and if the solution contains 2 arbitrary constants, then such a solution is said to be a complete solution. Next, notation. If you consider Z as the dependent variable and X and Y as the independent variables which we usually use in our examples, the partial derivative of Z with respect to X, dou Z by dou X is denoted by P, dou Z by dou Y is denoted by Q. These are first order derivatives. In the second order derivatives, dou square Z by dou X square is denoted by R, dou square Z by dou X dou Y is denoted by S, and dou square Z by dou Y square is denoted by T. So, this is the standard notation for first order and second order partial derivatives. Next, linear PDE of first order. So, we will be doing first order differential equations, partial differential equations which are linear. So, it is also called Lagrange's linear partial differential equation. So, a linear partial differential equation of order 1 involving dependent variable Z and 2 independent variables X and Y is of the form capital P into small p, this is capital P into small p plus capital Q into small q is equal to capital R, and we know that small p is derivative of Z with respect to X and small q is derivative of Z with respect to Y, and capital P, capital Q, capital R, they are functions of X, Y, Z, and this is called Lagrange's linear equation. So, it is a first order PDE because the highest order derivatives are of order 1, and the degree of the dependent variable Z and its derivatives dou Z by dou X and dou Z by dou Y is 1. So, it is a linear partial differential equation of first order. So, we can also represent that as capital P into dou Z by dou X. So, this is small p plus capital Q into dou Z by dou Y, this is small q, is equal to capital R. So, this is the standard form of first order linear partial differential equation. Now, the working rule to solve this first order linear partial differential equation, capital P into small p plus capital Q into small q is equal to capital R. Step 1, write the equation in the standard form, capital P into small p plus capital Q into small q is equal to capital R. And second step, write the subsidiary equations or the auxiliary equations which we represent as AE, given by dx by capital P is equal to dy by capital Q is equal to dz by capital R. These are the helping equations to find solution of the first order PDE. Step 3, find any two independent solutions of the subsidiary equations by using method of grouping or method of multipliers. We have to find any two independent solutions for these auxiliary equations by using method of grouping or method of multipliers, and the two solutions are considered in the form u of xyz is equal to a and v of xyz is equal to b, where a and b are constants. So, I am going to explain this method of grouping and method of multipliers after this working rule. Step 4, the general solution of the linear PDE first order is given by phi of u comma v is equal to 0, where phi is an arbitrary function, or you can also represent the solution as u is equal to f of v, where f is an arbitrary function, or you can write v is equal to g of u, where g is also an arbitrary function. Usually we represent the first, we take the first representation as phi of u comma v is equal to 0. So, following these steps we solve first order linear partial differential equations. So, in the method of grouping, in some equations it is possible that two of the fractions of the auxiliary equations can be grouped and integrated to obtain a solution. Consider dx by p is equal to dy by q if z is absent or cancelled from these fractions. So, when you are considering dx fraction and dy fraction, in this z should be absent or z should be cancelled. So, in such cases we can group dx and dy fractions. Now, integrating these two fractions, we get a solution u of xy is equal to constant. In the same manner, we see whether we can group the other possible fractions or not by considering dy by q is equal to dz by r, and dy and dz fractions can be grouped if x is absent or x is cancelled from these fractions. Now, integrating this, we get a solution of the form v of y comma z is equal to constant. Similarly, another combination is dx by p is equal to dz by r, and these fractions x and z fractions are considered when y is absent or y is cancelled from these fractions. Now, integrating this, we get w of x comma z is equal to constant. So, any two fractions can be considered for the solution of the first order PDE. So, this is the method of grouping. So, this grouping may be possible or may not be possible depending upon the given PDE. Next, method of multipliers. So, these are the auxiliary equations. Dx by p is equal to dy by q is equal to dz by r, and if possible identify multipliers L, M, N not necessarily constants, which means L, M, N may be functions of x, y, z, such that L into p plus M into q plus N into r is equal to 0. And if for this possibility of L, M, N, we can write the fractions as dx by p is equal to dy by q is equal to dz by r is equal to, so these three will be equal to a fourth fraction from the property of fractions L dx plus M dy plus N dz by Lp plus Mq plus Nr. Now, in our case, this denominator Lp plus Mq plus Nr is 0. So, the auxiliary equations will be equal to the fourth fraction L dx plus M dy plus N dz by 0. Now, grouping this fourth fraction with one of the three fractions, considering the first one, dx by p is equal to L dx plus M dy plus N dz by 0, and multiplying both the sides, we get L dx plus M dy plus N dz is equal to 0. And integrating this equation, we get one of the solutions as u of x y z is equal to a. So, this is how we can apply the method of multipliers for finding a solution of the auxiliary equations. Here, this is a basic case where multipliers are chosen such that Lp plus Mq plus Nr is equal to 0. Now, for another solution, similarly, we choosing another set of multipliers L1, M1, N1 such that L1P plus M1Q plus N1R is equal to 0, and after simplification we get the equation as L1 dx plus M1 dy plus N1 dz is equal to 0, and integrating this we get a solution as V of x y z is equal to B. So, we can apply method of grouping or method of multipliers depending upon the possibility to find any two independent solutions of the auxiliary equations. Now, example, solve P tan x plus Q tan y is equal to tan z. Now, compare this equation with the standard form of first order linear PDE, that capital P into small p plus capital Q into small q is equal to capital R. So, this is small p into capital P plus small q into capital Q is equal to capital R. Now, comparing, we have P is equal to tan x, Q is equal to tan y and R is equal to tan z. So, it is in the standard form and P, Q, R are identified. Now, auxiliary equations are dx by P is equal to dy by Q is equal to dz by R. So, that is dx by tan x is equal to dy by tan y is equal to dz by tan z. Now, we check for the possibility of grouping, method of grouping, and here we can consider or we can group dx by tan x is equal to dy by tan y, because z is absent in these two fractions. So, in dx and dy fractions z is absent. So, cross multiplying this or writing this in the form cot x dx is equal to cot y dy, or cos x by sin x into dx is equal to cos y by sin y into dy. Now, we can integrate on both the sides. So, log of sin x is equal to log of sin y plus constant as log a. The right hand side log of sin y plus log a can be written as log of a sin y, and on simplification we get sin x is equal to a sin y, or sin x by sin y is equal to a. So, this is in the form u is equal to constant a. So, u is the left hand side here, which is sin x by sin y. So, one solution is obtained. For the other solution, we can consider another set of another two fractions as dy by y is equal to dy by tan y is equal to dz by tan z. Now, these two are grouped because x is absent in these two fractions, only we have y and z functions. So, it can be written as sin y cos y by sin y into dy is equal to cos z by sin z into dz, and integrating this we get log of sin y is equal to log of sin z plus log b. So, right hand side is log b into sin z, or sin y is equal to b into sin z, sin y by sin z is equal to b. So, which we can take it as v is equal to b, where v is the left hand side. Now, two independent solutions are obtained for the auxiliary equations, and now we write the general solution of the first order linear PDE as phi of u comma v is equal to 0. So, u is okay. So, here is phi of sin x by sin y and v is sin y by sin z. So, it is phi of sin x by sin y comma sin y by sin z is equal to 0. So, here phi is any function of u and v. So, it is an arbitrary function. So, naturally these represent infinitely many solutions for the given first order linear PDE. Or if you want, we can write the solution as sin x by sin y is equal to f of sin y by sin z. So, this is another way of representing the general solution, or if you want, you can write sin y by sin z is equal to another arbitrary function g of sin x by sin y. So, these are various ways of representing the general solution. So, another example using the same method of grouping. So, solve y square z into p plus x square z into q is equal to y square x. So, the given equation is compared with, this is p, compared with capital P into small p plus capital Q into small q is equal to r. So, comparing, this is capital P small p plus capital Q small q is equal to capital R. So, P is y square z, Q is x square z and Q is the right hand side y square x. So, now write the auxiliary equations as dx by P is equal to dy by Q is equal to dz by R. So, that is dx by y square z is equal to dy by x square z is equal to dz by y square x. Now, we will see whether we can group the fractions or not. Here, if you consider dx by y square z is equal to dy by x square z. So, z is present in the denominator, but it can be cancelled. So, here these two fractions are considered because z is cancelled in these two fractions. So, we are left over with only x and y in these two fractions. So, dx by y square is equal to dy by x square, or you can write this as x square dx is equal to y square dy. So, z is cancelled in these fractions. Now, integrating on both the sides we get x cube by 3 is equal to y cube by 3 plus c, or x cube is equal to y cube plus 3c, or you can change this to another constant, x cube minus y cube is equal to 3c, or x cube minus y cube is equal to a. So, here a is nothing but 3c, another constant. So, one solution of the auxiliary equations is obtained as u is equal to a. So, where u is this left hand side. Now, for another solution again we try whether grouping is possible or not by identifying the fractions. So, if you consider dx and dz fractions here. So, dx by y square z is equal to dz by y square x. In these two fractions y is present and this can be cancelled, y square can be cancelled from the denominator. So, here y terms are cancelled in these two fractions. So, we are left over with only x and z terms in these two fractions. So, dx by z is equal to dz by x, or x dx is equal to z dz. Now, integrating on both the sides we get x square by 2 is equal to z square by 2 plus c, or x square is equal to z square plus 2c, or x square minus z square is equal to 2c, or x square minus z square is equal to b. So, you can compare this with v is equal to b, where v is this left hand side. So, in this case also both the solutions are obtained by the method of grouping. Now, the general solution is given by phi of u comma v is equal to 0. So, where u and v are substituted here, phi of x cube minus y cube comma x square minus z square is equal to 0, where phi is an arbitrary function. Another example using method of grouping. So, solve y square p minus xy q is equal to x into z minus 2y. So, the given equation is compared with the standard form. So, you can write the equation as y square p plus minus xy q. So, in the standard form we have plus as the operation. So, plus of minus xy x into z minus 2y. So, compare this with capital P into small p plus capital Q into small q is equal to capital R. So, capital P is y square, q is minus xy. So, it is a minus xy in this case, and R is the right hand side x into z minus 2y. Now, auxiliary equations are dx by p is equal to dy by q is equal to dz by r. Substitute p, q, r in the denominator. Now, identify grouping. So, here the first dx and dy fractions are considered. So, dx by y square is equal to dy by minus xy. So, here z is, these two are considered because, or grouped because z is absent. So, cancelling y from the denominator, we get dx by y is equal to minus dy by x, or x dx is equal to minus y dy. Now, integrating we get x square by 2 is equal to minus y square by 2 plus c, or multiplying with 2, x square is equal to minus y square plus 2c, or x square plus y square is equal to 2c, or 2c can be taken as a constant a. So, u is equal to a. So, where u is the left hand side, x square plus y square. Similarly, for the second solution, we check for the possibility of grouping. So, if you consider dy and dz fractions, so dy by minus xy is equal to dz by x into z minus 2y. So, here x is present in this, but x is cancelled from the denominator. So, for this reason we can group dy and dz fractions here. So, x is cancelled. Now, dy by minus y is equal to dz by z into z minus 2y, or rearranging the terms on left hand side and right hand side, z minus 2y dy is equal to minus y dz, or multiply z dy, and right hand side term is written on the left hand side as plus y dz is equal to minus 2y dy is equal to 0. Now, z dy plus y dz is an exact differential which can be written as d of y comma z. So, d of y comma z is an exact differential of yz, which is z dy plus y dz. Minus 2y dy is equal to 0. So, after writing the exact differential, we integrate and we get d of yz as the integration is yz minus 2 into y square by 2 is equal to b, or yz minus y square is equal to b. So, which is in the form v is equal to b and v is the left hand side. And now the general solution is given by phi of u comma v is equal to 0. So, phi of x square plus y square plus x square plus y square comma yz minus y square is equal to 0. So, where phi is an arbitrary function. So, in this as a summary, we have seen the definition of partial differential equations and the first order linear partial differential equations, which are Lagrange's linear equations in the standard form, capital P into small p plus capital Q into small q is equal to capital R. And to solve this, we have seen the working rule, and some examples are solved by using the method of grouping. So, in the next one, we take the examples with the method of multipliers, and we try to solve the first order linear PDE. Thank you.